Let's finish the analysis of this problem with parts C and D. For part C, we want to find the intervals of concavity and the inflection points. The way we do this is find a second derivative function. In order to have the second derivative function, you need the first derivative function. To get the first derivative, make sure you can utilize the chain rule, the derivative of the outside function evaluated at the inside function, times the derivative of the inside function. And of course, you know how to take the derivative of this function there. Now you have a first derivative in terms of a trigonometric function. Go ahead and take the second derivative. Once again, you need the chain rule, the derivative of the outside function evaluated at the inside function, times the derivative of the inside function. Then take the derivative of that function, add it to the first function, and now you have the second derivative. Now, using the language of trigonometry, you want to take advantage of your trig identities that you know as knowledge. So the cosine of a double angle, you want to manipulate this in such a way that it resembles the sine function. So use the trig identity and substitute there. Now you have the second derivative in terms of sine of x. And it's quadratic in form, so we factor. We take out the greatest common factor, and notice you get another factor that is quadratic in form. And you continue the factor. So your mastery of algebra involves factoring. Hopefully factoring is a reaction. And so when you see patterns of factoring, you just react to it and you know exactly what to do. After you've checked your factors, you realize that you need to find intervals of concavity. In order to do that, we need to set the second derivative equal to 0. Now we're ready to solve for D. Now, not all of these D's could actually be inflection points, or half of an inflection point, but the way you know if you have an inflection point is that we will test the second derivative on a number line. Going back to solving this equation, you have 3 factors that multiply to get you 0. Here's the first factor, here's a second factor, here's a third factor. Well, we already know that 2 is not equal to 0. So the only thing left to solve are these 2 equations on this interval there. And knowing your trigonometric values, you could actually translate the angles rather quickly in a matter of seconds, maybe less than a second. There they are. And this will separate your number line. And your number line only consists from 0 to 2 pi. And so you have your D values here. Put them somewhere on a number line. It doesn't have to be perfectly to scale. But notice you have how many open intervals? You're going to have 4 open intervals in which you need to test the second derivative. When you test the second derivative, you choose your own test values. Make sure you choose a test value between 0 and pi over 6 radians. I recommend pi over 12. And then where are you evaluating this? You're evaluating it here in the factored form of the second derivative function. That way you could determine whether it's positive or negative rather quickly. 2 times the sine of pi over 12 is a positive number that is less than 1. So that means this term here is negative, and this term here is positive. So you have positive times a negative times a positive will make this negative. And you continue to do this. I picked a test value of pi over 4. You could have picked other things. You probably could have picked 3 pi over 4 if you wanted to. But I decided to pick pi over 4 because pi over 4 is between pi over 6 and 5 pi over 6. And it works. Plug it into here. 2 times the sine of pi over 4 is simply root 2, and root 2 minus 1 is positive. And then this is obviously positive. So positive times a positive times a positive will get you positive. And we could do the same thing for pi. Evaluate the second derivative at pi, and notice sine of pi gets you 0. Sine of pi gets you 0. So this leaves you with positive times a negative times a positive. That is definitely negative. How about evaluating for a test value between 3 pi over 2 and 3 pi over 2 and 2 pi. I picked 11 pi over 6. Once again, substituting the second derivative, positive. Let's see. This is positive, this is positive. Sine of 11 pi over 6 is negative 1/2. This is negative. So positive times a negative times a positive is definitely negative. Now, what does that mean? Well, label that this function is now concave down on this interval here. Okay, this function is now concave up on this interval here. The function is now concave down on this interval here. And now, right here, the function is concave down on that interval there. That answer is part C. Now you just got to phrase it and write it. So what does part C look like? Part C is a lot of information. Part C consists of from this derivative here. I think I missed the first line, but I think you get the idea here. Part C requires an analysis that requires trigonometry, algebra, number line, test values, and of course you're using the calculus theorems appropriately. So that is part C. That is the information for part C. That's the answer to part C. How do we get an answer to part D? Well, the answer to part D, we want to know if there's actually inflection points. And the way you figure that out is see if the sign changes around one of these D values. So here's a D value. Did the sign change for the second derivative? It went from negative to positive. So it did change there. That means this will be the first half of an inflection point. How about for this value, for this D value? The second derivative sign changed from positive to negative. So this will be the first half of an inflection point. And how about this D value? This D value had the second derivative to be negative and then negative after. So this one is not an inflection point. So we're going to have two inflection points, and we evaluate the function at f to get the other half of an inflection point. So inflection points are ordered pairs, and there they are. You might want to keep track of these ordered pairs and put them in a t-chart. So you could put them back up here in a t-chart. You could actually put pi over 6 here, and then write negative 1/4. And then we could do 5 pi over 6 here, and write negative 1/4. And we're almost ready. In fact, I think we are ready to make a rough sketch of this function. Remember, this function is only available on the interval 0 to 2 pi. So that's why there's a bracket here. That's actually 0 to 2 pi. And notice we took part A and B and indicated when the intervals, or I should say when the function is increasing. So that's what this is saying right here. Now you're going to put two pieces of information together. When is the function decreasing and concave down? So if it's decreasing and concave down, you'll get this shape here. Now it's decreasing and concave up. You'll get this shape here. Then it went increasing and concave up. Then you get this shape here. Then it still is increasing, but now it's concave down after a what? After an inflection point. So there is a change in concavity there. What happens at this? Notice between 5 pi over 6 and 3 pi over 2, it's increasing and concave down. It gives you this shape here. Notice between 3 pi over 2 and 2 pi, it's concave down and decreasing, so it gives you this shape here. Now putting those pieces together and then labeling, you don't have to have a perfect scale, but you want to scale it in such a way that you do get a good sketch of this graph. Drew out 2 pi because that's how you graphed a lot of trig functions. Given interval was between 0 and 2 pi, it makes sense to dissect 2 pi as well as you can. Notice I just spaced out increments of pi over 2 and then plot as many ordered pairs as possible to the best of your ability. Just plot all those ordered pairs, put them here, put all those ordered pairs here, and then use that shape that you got from the second derivative and try to just connect the dots. And you have a sketch of the function. Even though your sketch is not to scale, it's a pretty decent sketch just by using the first and second derivatives and finding more and more ordered pairs. You're always welcome to pick more ordered pairs, and it will give you a more accurate sketch of your function. If you do pick more ordered pairs, just indicate them in a t-chart. Organize your work, organize your data values, put them right here, make your life a little bit easier. And of course, use lots of paper.